Give me a sec.
Yo, this is D-Dog David. How y'all doing?
Hey guys, as you can see, I have my assistant here with me today for the video about spectroscopy. So spectroscopy, hopefully you recognize that the first part of the word spectro comes from spectrum, and that's when we're talking about things that have to do with light. So let's talk about the interaction between atoms and light. So light is really the key to understanding our modern version of the atom. Remember, we talked about that cloud model of the atom. And so it has wave properties, and you probably learned a little bit about that, but it also has particle properties depending on the way that you measure it. And we call a packet of light a photon. So any of you Star Trek fans, photon torpedoes, that's what they are. So the first thing we need to look at is the electromagnetic spectrum. This is in your yellow packet. You should pull it out, pause if you need to, and just take a look at this so that you can see in front of you what it looks like. All types of electromagnetic radiation are light. And you can see, if you look at the visible light section, that it is really a very small part of the electromagnetic spectrum when you look at all the other types of light. There are different things that I'm sure you've heard of. Things like x-rays. You go to the dentist, you get an x-ray, or if you've ever broken or thought you've broken anything. Ultraviolet light, I'm sure that you guys know that that comes from the sun. Microwaves, infrared, that is used in things like scanners and that sort of thing when they scan price tags. Radio waves, I'm sure you're familiar with those. I'm guessing that most of you have a cell phone. I know I like mine. So radio waves are how we transmit radio and cell phone signals. When we talk about wavelength, we have to think about how we measure it. So wavelength, what unit does that imply? Hopefully you said meters. It's the distance between two equivalent points on a wave. So if you see at the top of that little picture, it's got crest to crest, that's the top of the wave, or at the bottom, trough to trough. And those are the equivalent points on a wave that we use for measuring. And wavelength has this funky little symbol. It's a Greek letter, lambda, and that is the symbol that we use for wavelength. And if you think about length as a measurement, remember that we always measure it in meters, so some type of meters. Nanometers, picometers, you're going to get into some of those prefixes where we haven't used them, or you may not have heard of them before, but we're using them now. So make sure you go back and buff up on those before the quiz. So let's talk about the characteristics of light. There's also frequency. That's not a V, that's a Greek letter nu. So V, it looks like a V when you write it. It's the number of times a particular point on a wave passes by an observer in 1 second. So if you have somebody standing at the end of the waves on the left-hand side of the screen, it's how many times each of those waves passes by that person in 1 second. So you can see that there are some differences in the wavelengths and the frequencies of the different colored waves. So think about which one has the highest frequency. Hopefully you said purple. Some people think it looks pink, that bottom line. How about the lowest frequency? That would be the red. And if you think about it, look at the wavelengths. So we said that the red had the lowest frequency. Does it have a long or a short wavelength compared to the purple one at the bottom? It has a much longer wavelength. So we want to think about that relationship between frequency and wavelength. So the frequency is measured in hertz. Hertz is also equal to 1/seconds, and that'll be important when we do calculations. So wavelength and frequency are inversely related. If wavelength increases, frequency decreases. As one goes up, the other goes down. And we have an equation for the relationship between frequency and wavelength. It's C equals lambda nu. So C equals wavelength times frequency. And C is actually the speed of light, which is a constant. That means it never changes. Light always travels at that speed, 3.00 times 10 to the 8th meters per second. And then let's talk about some characteristics of light. There are lots of frequencies and wavelengths of light, and you kind of saw that on the little chart from your reference table earlier. And you can see again, this one looks a little bit different, but that visible region of light is really small compared to all of the other parts of light. So we can only see very small sections of that light spectrum, but there are lots of other important types of electromagnetic radiation or light. One photon of light really can only transfer a certain amount of energy. And the way that we figure that out is energy E is equal to H times nu, V the little Greek letter nu. So E is the energy of that one photon. H is called Planck's constant. And again, when we say it's a constant, it never changes. And that is 6.626 times 10 to the negative 34th joules times seconds. And then nu, the little v, is our frequency. So that might be given to you in a problem, or you may have to calculate it. And energy, if you think about it, if frequency increases and we're multiplying it by a constant, then energy will increase. So those ones are directly proportional. If one goes up, the other goes up. Let's go back to this electromagnetic spectrum now and think about which light can do the most damage to you. So think about what we know about wavelength, frequency, and energy. Pause the video and think about those relationships. Okay, so if you think about it, the highest energy is going to have the highest frequency. And there's nothing on this chart about frequency, but if you look, we know the highest frequency will have the shortest wavelengths. So the shortest wavelength types of light are to the right side. The short wavelength high frequency has the highest energy. And if you've ever heard of someone having cancer and having gamma knife radiation, that's a very strong type of radiation that's used to treat tumors, a lot of times brain tumors, and it is extremely powerful and dangerous. So you can see the sun, the ultraviolet light from the sun, has higher energy than visible light, and we know that it damages us because we protect ourselves from it with sunscreen. X-rays, you go to the dentist to have an X-ray, first thing they do is put that lead apron on you. And then the person who's taking the X-ray steps out of the room to the other side of a lead wall so that they're protected from those X-rays. All right, so let's look a little bit more at those relationships and just kind of solidify that. So wavelength and frequency are inversely related. One goes up, the other goes down. It's a mathematical relationship. Frequency and energy are directly related. So let's think about what the relationship must be between wavelength and energy. If we know that wavelength goes up and frequency goes down, energy goes down. So if wavelength goes up, energy goes down. They are inversely related. Let's look at a couple of practice problems. So in this problem, it's giving us a laser pointer emitting light at 532 nanometers. And it's asking us to tell which region of the spectrum the light is found in. So it's asking whether it's radio waves or infrared or gamma rays. And then if it's visible, if it falls in that really narrow visible range, it's asking us to give the color. So if it falls anywhere in this little narrow range there, it's going to ask us what color it is. So if you determine something's visible light, be prepared to find the color. So let's start off by looking at this chart. You'll notice here it says that the measurement is in meters, and in our problem our measurement is in nanometers. So we're going to have to go back and convert the nanometers to meters. So if you haven't looked at those prefixes lately, you might want to brush up on them before you see them on a quiz. So let's take a look at that conversion. So we're going to convert from 532 nanometers we're going to set up our conversion factor. We want nanometers on the bottom to cancel. We want meters on the top. Hopefully you remember your scientific notation. Nano starts with N, it's -9, and that always goes with the base unit, so the one without the prefix. So 1 times 10 to the -9th. And then we put the 1 with the nanometer. And when you punch that into your calculator, you should get 5.32 times 10 to the -7th meters. So now what we want to do, I'm going to go ahead and click that off so we can look at the chart. We're going to come down here and look at our information on our spectrum. So what you want to do is you want to find 10 to the negative 7th meters. That's right here. And because it's 5.32 times 10 to the negative 7th meters, we know that it's greater than 10 to the negative 7th meters. And so you want to look at the direction of your exponents. The less negative they are, the bigger the number is. So it's going to fall somewhere in this range. It says it's 532 nanometers, or 5.32 times 10 to the negative 7th. So we want to come down here and look. It does fall between 4.0 times 10 to the negative 7th and 7.0 times 10 to the negative 7th. So we need to find out where 5.32 falls. So 5.32 times 10 to the negative 7th, if you look at these little tick marks here, 5.32 falls between 5.7 and 4.9. So this would be visible light. And it would be green. And you would need to give me both of those answers to get full credit for a problem like this. All right, so now that we know our wavelength, let's do a little bit more with this. Okay, so now we're being asked to find the frequency and the energy of that light. So let's look at that. We know our wavelength, we've already calculated that in meters. So let me just write it up here. And then if we want to find our frequency, our relationship between the wavelength and the frequency is C equals lambda nu. Okay, and we want to solve this problem for the frequency first. We know the wavelength, C is a constant, the speed of light, so we want to get nu by itself. So we're going to divide both sides by wavelength. So just like we were doing when we were calculating densities, these two will cancel, and we know that nu will equal C divided by lambda. And then it's just a matter of plugging in what we know. So we know that the speed of light is always 3.00 times 10 to the 8th meters per second. And then we're going to divide that by our wavelength, which is also in meters, 5.32 times 10 to the negative 7th meters. Now let's watch what happens to the units here. The meters will cancel. Now remember that seconds is below the line. It's in the denominator. So our unit is going to be 1 over seconds. Pause and punch that into your calculator. And what I got for that was 5.64 times 10 to the 14th. Remember that 1 over seconds is the same as hertz. So if you see hertz in a problem, hertz is the same as 1 over seconds when it comes to your units. Now we also need to figure out, it's asked us for the frequency, but it's also asked us for the energy. So E equals h nu. We can't directly find energy from wavelength, we have to find the frequency first, but now we found it, so let's go ahead and plug that in. Remember that h is Planck's constant, 6.626 times 10 to the negative 34, and that's joules times seconds. And then we're going to plug in our frequency, 5.64 times 10 to the 14th. And I'm going to leave that unit as 1 over seconds, and I'll show you why as we deal with our units here. As you can see, we've got joules times seconds, so this second will cancel this seconds, and then we're left with our unit of energy, which is joules. And then when you calculate that in your calculator, I got 3.74 times 10 to the negative 19th, and don't forget the negative. Remember to check your answers for these problems for sig figs. So if yours is not matching up exactly with mine, double check your sig figs. So go ahead and read through the problem. So in this problem, it's giving us two pieces of information, and it's asking us to find a wavelength. So we've got to figure out which of those numbers is important to the problem. One tells us the band that they're developing new cell networks in, that's that 700 megahertz. The other one tells us specifically where Verizon's band starts. That's the important number in this problem, and it asks us to find the wavelength of that light. So let's go ahead and calculate that. So we know that our relationship between wavelength and frequency is defined by C equals lambda nu. And if we want to get wavelength by itself, we need to divide both sides by nu. And nu will cancel. And then we know that wavelength, or lambda, is equal to C divided by nu. And then we can just go ahead and plug in our information. We know that C is the speed of light, which is a constant, so 3.00 times 10 to the 8th meters per second. And nu is the frequency. Now, because this is meters over seconds, we're going to have to get hertz to our base unit. So let's go ahead and convert that. 777 megahertz. And we want to convert that to hertz, the base unit. So megahertz on the bottom to cancel, hertz on top. And remember that mega is 1 times 10 to the 6th. That goes with that base unit, so in this case it goes on top, remember not always. And then a 1 with the megahertz. And when you punch that into your calculator, you would get 7.77 times 10 to the 8th. And the megahertz cancels, so you're left with a unit of hertz. Just a reminder, stop and pause the video and punch these in for yourself to make sure you're getting the same thing on your calculator as I am. So let's plug that right in, 7.77 times 10 to the 8th hertz. And remember that hertz is the same as 1 over seconds. So let's just deal with that unit for now. So I'm going to mark this out. So 1 over seconds will cancel here with this 1 over seconds, because meters over seconds, remember that meters per second is the same thing as meters times 1 over seconds. So that 1 over seconds will cancel, and you don't need to show this particular work, but you do want to show the units canceling in your equation. And when you plug that into your equation, you end up with 0.386 meters. So your unit that's left is meters. Let's finish this problem. There's a little more to it. So on the next one, it's the same problem, but now it's asking us for the energy. Fortunately, we know that we can't find energy directly from wavelength, but it's given us the frequency in the problem. So we can go ahead and just calculate that now. So we know that our equation for energy is E equals h times nu, and we know that h is Planck's constant, so 6.626 times 10 to the negative 34th joules times seconds. And then we know from our last screen that our frequency, we want it in hertz, not megahertz, so we're going to use 7.77 times 10 to the 8th, and we're going to call that 1 over second. Remember that hertz and 1 over second are interchangeable. Now if you watch what happens with the units here, these seconds cancel these seconds, so we're left just with joules, which we're happy about. That's our unit of energy. And then when you multiply those numbers in your calculator, pause and do that, you get 5.15 times 10 to the negative 25th joules. If you have questions on these, ask for help in class. I'll see you there.